Today's topic is about circles and problems related to circles. Of course, we're going to also using Pythagorean theorem to solve the problems, some problems. Okay. Now about circles, right? What we should know about circles? Okay. Circle has a tangent line. Okay, has a tangent line. So so this, what is the definition of tangent line? Tangent line is a line touch the circle at only one point. Okay. Now, if you connect the center to the tangent point, this angle must be 90 degrees. Okay, because they're equal position. See, both sides should be equal, right? Because otherwise, it's not going to be tangent line. So this angle must be 90 degrees. So that's the first important property we keep in mind. Another important property about circle is it's not easy to prove. Okay, you fix 2 points. You fix 2 points, A and B. Okay, and then randomly pick up point C. Sorry. You draw the line between those 2 points. Yeah, and you get angle alpha. And you notice that this angle alpha is independent the location of the C. Wow. So if you move the point to here, you still get the same alpha. Okay, and what is that alpha? The alpha is equal to, if you connect to the center, so alpha must be equal to half of the beta. Okay. Yeah, this is not easy to prove, but as long as you can show it's independent of the location of the C, then alpha is going to be half of the beta. I think it's a little bit easy to find out, because you use a special case. You can show that, yeah, you can show that alpha is going to be half of the beta. Okay, let's take a look at this. Okay, let's take a look at this case. Okay, this is a beta, right? And then you just as the middle of the line, right? So you draw this line. Okay, and y alpha is going to be half of that. The reason is as follows. Okay, now you can change the location a little bit. Okay, so yeah, let me change the location a little bit. So we can do that in general case. Let's see, how do we prove that? Okay, how do we prove that? Okay, so you can draw the line, yeah, like this, right? Okay. No, yeah, that takes too much time. All right. I just want to, we can, yeah, do this a little bit later if we have a special time. Okay. So I'm going to apply this results to solve some problems. The third property, let me list all of them first. The third property is, if this is radius r, okay, this is angle theta. Theta will be, theta is in radians. Okay, do you know what does radians mean? Yeah, radians means if it's 180 degrees, should be changed to the pi. Okay, then the area of this sector, okay, is given by the formula theta times r squared. I think it should be divided by 2, because when theta is 2 pi, it is you get a whole circle, so the area is pi r squared, and this arc length is theta times r. That's true. Okay, so those are the 3 important formulas about the circles. All right. All right, so now we are going to take a look at the following example. Okay, so we have pictures like that. Okay, this is called called a rhombus. Okay, so that means those four sides are equal. But it's not parallelogram. Okay, those four sides are equal. Okay, so what we know is this has two diagonals. Okay, they're perpendicular, right? So the length of two diagonals are 24 and 10. (24 units and 10 units). Okay, we want to find out the radius of the inscribed circle. Right, so the inscribed circle is here. Let's use a different color. Okay. All right, so how do we solve this problem? When you get a geometry problem, right, like that, the first thing you have to do is to connect important points. Then you will realize there's this, names a variable for each side. Maybe you get a triangle, and you can apply the Pythagorean theory to the triangle. So important points, I think this is a tangent point, right? So I should connect it. And then then this is a right triangle, right? So what they actually get here is a right triangle. Okay, you get a right triangle like this. Okay, and then the radius is going to be the height of this right triangle. The bingo, so you should know that, right? So actually, all you need to do is the right triangle. This side is 5. This side is 12, right? Because the diagonal, the length of the diagonal is 24, so half of that. And then you can also use a Pythagorean theory. I think you're going to get 13. Okay. Then you draw the line perpendicular to that point. So this is called h, or the radius, right? So you can use a area formula to find out. So the area of this triangle is going to be half of 5 times 12. This also is half of 13 times r. Okay. So I is going to be, I is going to be 5 times 12 divided by 13. Okay. You can also use a similarity triangle to solve it. Okay. But this is the easiest way to do. Okay. So that's it. You see, sometimes the picture looks very complicated, but if you connect the important points, key points, then you will see few right triangles and try to apply the Pythagorean theory to the right triangles. Okay. You can also use a similarity of the triangles to determine the radius. All right, our next problem is a circle of radius size inscribed in a regular hexagon. What is the area of the hexagon? Okay, and I can specify the radius. Okay, a circle of radius, okay, r equals 1 is inscribed in a regular. When we say regular, means all the sides are equal. Hexagon, right? So question is, what is the area of the hexagon? This should be larger than hexagon, okay? This should be larger than the circle because hexagon looks like that, right? And the circle is inscribed in the hexagon. It touches 6 sides of the hexagon. Okay, so the area of the circle is pi r squared. The area of the circle is pi r squared. So r is going to be 1. So you don't need to specify the value of r right now. Okay, let's find the area of the hexagon in terms of the radius. Okay, again, I tell you, connect the important points. This is the important point, right? The tangent point. The vertex is also the important point. So after you connect those points, you will see an equilateral triangle, right? You will see an equilateral triangle. And write 2 identical right triangles, right? So you can apply the Pythagorean theory to this problem. How to do that? Okay. See, it's all you have to do is find the base, right? The radius. Okay. So this side is A, right? So as you can see, as you can see that the height, let's try this. This height is radius, right? And so this is a special right triangle, 30 degree and it's 60 degree, right? So the other side, this is the A actually. This is half of A, right? Right? Edge length, right? So then then you have the relationship, right? R over A is supposed to be square 3 over 2, you immediately get. So you can get A is going to be 2 over square 3R. So if the radius is given, then the edge length of the hexagon is given. Okay. Then the hexagon consists of 6 identical right triangles, identical equilateral triangles. So the area of the hexagon, okay, equals 6 times the area of the equilateral triangle, right? So equilateral triangle is going to be square 3 over 4 times A squared. That's the formula, okay? Then you plug them into, then you get 6 square 3 over 4, 2 square 3 R squared, and then you simplify it. I think you will get 6 square 3 over 4. Here's 4 over 3, and R squared, 4 cancel out. So it's 2 square 3 R squared. So you find the relationship between those two, okay? And I'm pretty sure this is larger than the area of the circle inscribed in this hexagon. So it means 2 square 3 is larger than pi. You can check that, okay? It's question, right? And otherwise, there's computation mistakes. Okay. Yeah, this is the area of the circle, right? And square of 3 is 1.7 something. So 1.7 times 2, right? It will be, 3.4, which is greater than 3.14, right? Yeah, so that's why it's true. All right, so this is, you see, did we use a property, the tangent line, right? The tangent point to the center is perpendicular to the tangent line. This is a property used over and over again, right? Yeah. All right, so now you have I want you to try this problem. We have 2 congruent circles, 2 congruent circles. Yeah, those are 2 identical. Okay. And I don't know their radius. So what I'm doing is I draw the line from the center of one circle and tangent to another circle. Okay, this is a O. That's the tangent point T. Okay. I can measure these 2 points. So the distance O and T between O and T is 2 square root 3. Okay. Based on this information, can we find the radius? Okay. So I want you to try. Okay. Find the radius of the circle. Yeah, I want to have a try. Okay. Remember what I told you. Connect the important points. Okay. What are important points here? Tangent point, center of circles. Okay. Then you will maybe get some ideas. All right. Anyone have answers? Nina gave me answer. Great. Okay. So let's draw the lines. Okay. Important points. Here's another point. The center. Then I connect the two centers. Then I connect the center between. Right. So you get a right triangle. That's it. You get a right triangle. Then you, the radius is unknown. So you put a radius here. Here's R. Here's here. It's 2 square root 3. Right. So now for this right triangle, you can apply the Pythagorean theory. So 2 square root 3 square plus r square equals 2r squared. That's it. Okay, so you get, here you get 12 r squared. Here's going to be 4r squared. Right, so now I have a 3r squared equals 12, r squared equals 4, r is going to be 2. Good. No, it's not equal to 3r. How do you know that's 3r? Okay, right, 2 square root 3 is not equal to 3r. Okay, if it's 3r, then you already find r, right? Yeah, nobody told you it must be 3r. But if you have two circles tangent to each other, then if you connect them, it doesn't matter which one has a radius, which is another one has a radius, smaller radius. But if you connect the two center, it must go through the tangent point. Okay, and this capital R is related to R. So the distance between the two center will be the sum of those two radius. Okay, this is a OP, right? So OP is going to be capital plus little. That's it. Okay. So if you choose the circle, small circle, larger circle, doesn't matter. And maybe have a giant circle here that connect. Yeah, if you connect those two centers, it must go through the intersection as a tangent point of those two circles. Okay, our next problem is as follows. We have an equilateral triangle. That's equilateral triangle, right? Okay. So inside this equilateral triangle, I have a large circle inscribed. Okay, that's okay. Then I have a smaller circle inscribed here. Okay, clear, right? So the larger circle has a radius capital R. The smaller circle has a radius R. So we want to find out the ratio of them. Okay. You can scale this equilateral triangle, but the two circles changes proportionally. Okay, so you're able to find the ratio of them. All right, how do you solve this type of problems? Well, let me redraw the picture again. Okay, make it a little bit larger. Did I tell you connect the important points, right? Connect the important points. Okay, center, vertex, center, connect them. Okay, and this tangent points, you connect them. So you will get two right triangles here, right? Okay, so let's measure. Yeah, let's measure. This is a, that's a B, that's a C. Okay, I'm going to calculate. Yeah, this A B C D. Okay, so this is a equilateral triangle. You have to use a proper equilateral triangle. That's a 30 degree, right? Now, if this is capital R, this is little r. So AB is supposed to be 2R. Do you agree, right? Yeah, AB is equal to 2R because a 30 degree triangle. 30 degree triangle, right? If this is R, that's must be 2R. And similarly, the smaller one, okay, DB is also little 2R. Okay, that's it, right? But we can calculate AB in the following way. AB is also going to be, oh my God, let me bring back the file. Sometimes it just disappeared. Okay, cool. Okay. Yeah, you have to calculate. The AB in different way. You add them together. Okay, so AB is going to be AD plus DB, right? DB is 2R. What is AD? So this is 2 capital, right? AD is actually, AD is the distance between two centers. Should be R plus little r, okay? And this is 2R. So that's the relationship, okay? So now it's clear, okay? You will get I equals 3R, okay? So the ratio is going to be 1/3. Okay. Okay, so it's going to be 1/3. I wanted to work out the next problem. The next problem is as follows. Okay, you have a circle, then there's inscribed equal red triangle. Then you have another circle inscribed. Then, right? Then you have another equal red triangle inside. Then another circle inscribed. Just keep it going like this, okay? And the circle is getting smaller. Okay. So what do we, yeah, the circles labeled by C1, C2, okay? That's a circle C1, that's a circle C2, that's circle C3, okay? If, yeah, so what I want to do is find the area, yeah, find the ratio of the area of, you know, C, yeah, C, yeah, C1, C2, and over the area of C1, okay? And similarly, this should be the same as C2, C3, I think, yeah. So because it's a repeating, yeah, it's a repeating. Right. Yeah, you see, when you look at C2, just look at C2, then you draw equal trying to get C3, right? So it's the same, okay? You can also, I'm gonna ask you to find the area of a C3 over the area C1, okay? Okay, those are the, please work on this. Right. Let's see, anyone has answers? Okay, nobody yet. Now you can describe the radius by, right, different radius by circles. Okay. So so you can connect. So I told you, connect the important points. So this is center, all the way to here, right? And draw the line. Okay. So what do you get? Right? What's the relationship between R2 and R1, right? What's the relationship between R2 and the R1? Okay, if yeah, let's find out just to find this. Okay, so let's redraw the picture here. Equate the triangle and have another triangle inside, another circle, right? So let's take a look this picture. Okay, so I'm going to get this is R1, this is R2, but this equate a triangle, right? So it's clearly R2 equals half of R1. That's it, right? Because this is a 30-degree triangle. Okay, it's a 30-degree triangle. Okay, and similarly, if we continue this repeating this process, R3 is going to be half of R1, R2. Okay, right, and that will be a quarter of R1. So as long as you know the relationship between among radius, then you can figure out the ratio of the areas. Okay, so that implies pi R2 square of a pi R1 square is just equal to a quarter, right? This implies the same, yeah. Pi R3 square of a pi R1 square is just equal to 1/16. Okay. So the area shrinks quickly. Okay, you could draw more circles and zone in, you have billions of circles. It's getting tiny. Okay, it's getting small quickly. Okay, this is an interesting picture, but the circle, okay, so whatever is the circle you get inside, the area is going to be a quarter of the area of the largest circle, right? Yeah. See, draw a larger circle and draw equal triangle, draw another circle. The area of this smaller circle is going to be the quarter of the area of the larger circle. Yeah, okay. Now our next problem is I put the 3 congruent circles together. Okay, we can do that, right? Those are the 3 circles with radius, fixed radius. Okay. 3 congruent circles are tangent to each other. Okay, and this is called a radius. Okay. So there's a tangent point here, right? Tangent point here. Those are the tangent points. Okay. I really want to find out the area of the shared region, this black one. Yeah. Find the area of the shared region. Okay. So the region looks like that, right? But this is not a triangle. How can I do that, right? This is not a right triangle. How can I do that? You probably have to use a subtraction, because usually if it's a region in the irregular shape, right, to find the area, you cannot use any formula. So what they do is you use a subtraction method to look at the region surrounding region, and then you subtract the area of the other part. Okay, so how can I do that? Remember, we just connect the important points. Then you connect them, and you get an equilateral triangle. Okay, so those lines passing through those tangent points. So you get an equilateral triangle, and right? How do we draw this? Right? So the equilateral, you know how to find the equilateral triangle, the area. But how about each sector here? So each sector have a 60 degree, right? 60 degree. So those three sectors, you can find the area. So use a subtraction, the area, and this R, right? So the area of this shaded region, okay, is going to be the area equilateral triangle, which is a square of 3 over 4, and a squared is 2r, minus the area of the three sectors. But those three sectors, you can put them to form a semicircle, okay, right? Because 60 degrees, 60 degree. So so semicircle is pi r squared divided by 2, right? Yes. So this is the answer. Okay. This is the answer. You cannot simplify. It's going to be square of 3r squared minus pi over 2r squared. And this is supposed to be positive number. Okay. And the square of 3 is larger than pi. You know, remember we already said that 2 square of 3 is larger than pi, right? So this is again, you know, it's an interesting number, yeah. Difference, yeah. Okay, so this is going to be half of 2 square of 3 minus pi r squared. That gives the area. Okay. Yeah, maybe this is a little bit difficult. What else I can do? Okay. I still use these 3 congruent circles. Okay. This time, I'm going to put a belt on that. Okay. Okay, tight. I want to find the area of this. Okay. Yeah, that's the second question. So the radius, yeah. So 3 congruent circles of radius. Okay. Find the area of the shaded region. Okay. I think all you needed to do is find one piece of that. Okay. Because there's a one in the middle, we already find out, right? And the other 3 are identical. Okay. The belt, okay. 3 congruent circles. One is a tangent to each other. Second is a belt is tightly around them. Yeah. Okay. So find the area. Okay. Well, here's the point. Okay, so it's not difficult. Okay, but you have to use the properties I told you. Okay, properties of the circles. Okay, I let you to have a try first. Right. Nobody gave me the answer yet. So let me try to work on this first. Okay. So this is just two circles. So I just draw those two circles. A line is tangent to this point. So those are 2 point tangent. Right? Right? So the belt, touch those 2 points. Then around the circle and going in the other direction. Okay, so this is the center, this is center. Connect the points. Since this is a right triangle, so what do you get? You get a rectangle. That's it. So this is R, this is R, this is R, this is R. So the area of that part, okay, the area of this part, okay, of this shaded region, okay, I call the, this shaded region. As long as you find the area of this is you're done, right? So it's going to be the area of the rectangle, R times 2R, minus the area of the other 2 halves, quarter of circle. But those quarter of circle also form semicircle. So it's pi over 2 times R squared. That's it. This is going to be 4 2R squared minus pi over 3R squared. You can take it out. Okay. So that is our the final answer will be add them together and answer, right? Add them together. So I'm not going to do that. See, as long as I keep saying that, as long as you connect important points, you will see how to solve the problem. If you just sit there, don't do any drawing, then you cannot, right? All right. So for example, here's another example. Okay, I have a larger circle, and inside this larger circle, I'm going to put 4 circles. Let me draw. It's harder to draw that. 4 circles. Yeah. Four congruous circles in square it. Okay. So those 4 circles, the radius capitals R, right? And this larger circle, the radius capital R. So can we find the ratio of them? Right? So you have a larger circle. It's in square 4 small circles. Why we have to solve this problem? Think about that. If you have a cable, right? Inside the cable, you put 4 smaller cables, you bond together, and you really want to know how the ratio, the cable, the larger cable, right? This if you know the radius, right, capital R, can you figure out the radius of smaller circles? So there are 4 lines, right, inside. Okay, so this is a very realistic problem, right? We needed to figure it out. Okay, then this becomes geometry problem. If you graduate from, middle school, you're supposed to be able to solve this problem. Okay, and it's surprise, it's not that complicated, right? You don't need to even measure, cut it and measure it. You can do the calculation. Right, you can do an estimate. So let's draw this, connect the important points. Okay, I repeat 3 times important points. So you get, square, right? And the center of the larger circle also is important. So maybe you connect them. It goes like this, right? That's all I get. I get so many, and the tangent points, right? Tangent points. So you got so many, yeah, you get squares, you get the right triangles. Then the problem is solved. Why it's solved? Okay, you can you can draw the Yeah. Do we have other important points that we have to use? Yeah, I think this is the important points, right? You can extend it. Okay, because of certain points. Okay. Okay, so now I apply the Pythagorean theory to one of the triangles, right? The triangles. I'm going to copy this here. All right, so this is a little clear, right? And how about no? That's not working there. We have to use this two. This is called isosceles right triangle. Okay, this is R, right? How about the other side? The other side, you see, this is a little r. This from here to here is capital R. So the difference is capital R minus little r, right? So capital R minus little r. All right, then you can solve the problem because this is also a right triangle, right? This is also right triangle. So capital R square, right? And the plus capital, right? Should be equal to R square. All right, so that's it. Right? So 2 of this is a 4R square. Let me take, divide by 2. Then you take square root. Then I have a capital I equals 1 plus this. Okay. So therefore I find the ratio. The ratio is going to be 1 over 1 plus square root. Okay. And then you can also change it to this. Okay. Well, it doesn't matter which form you use. So you find the ratio. Okay, you can do estimate. Okay, you can estimate this using calculate. So then it's not a fraction. Okay. So I said you have to connect the important points. Okay. Okay. Our next problem is still about circle with a so larger circle, and inside the larger circle on this diameter, I'm going to draw 2 smaller circles. Okay, sorry. Then they already occupy lots of space. Then I draw the little circle here. Okay, this is radius R. This is a capital R, right? So I want to find out the ratio of these two. Okay. So largest, you have 3 circles in a different size. Okay. But it's easy to know this. The radius, the largest circle has a radius capital R. The small circle has little r. That's radius little. So you find the ratio of them. Okay. Find the ratio. Okay. How to solve this problem? Well, I said connect the important points. I repeat it many times, right? Connect the important point. So this is in the middle, connect them, right? And those 2 centers connected. Then you're done. And you get a right triangle. Then you get a right triangle. This is a right triangle. And you have to express each side in terms of little r and capital R. Then you apply the Pythagorean theory. Okay. So let's take a look at this triangle. Okay. This side will be half of R, right? This side will be little r plus capital R, right? Then how about the other side? The other side will be R minus little r, because from here to here is a capital R, and from here to here is a little r. So the difference will be this. As long as you express three sides in terms of capital letter R, and then you apply the Pythagorean theory. Right, then you solve it. That's it. It's a quarter of capital R squared. R squared minus 2R lit R plus little r squared. Okay, so little r squared cancelled out, capital R squared cancelled out. And the quarter of R squared equals 4 little r capital R. Okay. Okay, hold on. Let me double check my computations now. I think I made a small mistakes here. This is this side is half of R, because from here to here is half of R. Yeah, so that is a half of R. Add them together. So that will be no, and I cannot cancel. I cannot cancel this. Okay, so let's keep R squared, and this is a half of R squared. That, yeah, be careful about this, you know. Yeah. Okay, when I draw the picture here, you see the sum of the two radius of the circles, and this is already, it's a half of R here, right? Half of R, not just capital. Okay, so now, now you have this, right? So let's redo this. Yeah, let's simplify it. Okay, let me simplify this, both sides, then I do them. The left-hand side is going to be, left side is going to be 5 over 4 R squared minus 2 little. Okay, so right-hand side, here's R squared over 4. Okay, so I move this to the left-hand side, this to the right-hand side, so I get capital R squared and 3 little, right? Then it's clear that, okay, just recall 1/3. Good. So we solved the problem. Okay. Our next problem is a very typical problem. It's about it's a very typical problem. What I'm going to do is, then I have an equalated triangle. Okay, no, not equalated. I just very general. The problem here is equalated triangle, but I'm going to draw a very general. Okay, so this is triangle ABC. Okay, so I have a circle inscribed in this triangle, and so express R in terms of ABC. Okay. Yeah. Okay. How to do that? Well, you connect the important points. Connect the important, right? Those are tangent point. Tangent point. Tangent point. So you get right triangles. Not right, get a 90 degree. But that's not good enough. We have to still have to connect those important points. So you decompose the triangle into 3 triangles. This time I'm not going to use a right triangle because it's not difficult, not easy to find out. as the area, okay? So the area of the triangle, okay, area of this triangle, A, B, C, okay, is going to be by the Heron's formula is going to be S minus A, S minus B, S minus C. Here, S is going to be half of A plus B plus C, right? But on the other hand, it's area of the three triangles. So it's going to be the area of the triangle AOB plus the area of the triangle AOC plus area of the triangle BOC. Okay. So for each of them, you have the following. Okay. You have half of AOB is half of C times the radius R. The radius is going to be the height of the triangle, right? And this will be B times R. This will be C times R. Okay. And you will see that you will get A plus B plus C times R. This is nothing but just SR. Okay. So now you find the radius. Radius is going to be S minus A, S minus B, S minus C. But if you move S into the radical, you will get S over S squared. So actually, so you can get a very general formula. Great, looks good, right? So in the future, you know, if you have a triangle and the three sides are equal, the three sides are given, then you can find the radius of the inscribed circle using this formula. Okay, this is it's an interesting formula. Okay, and S is half of the parameter. Okay, half of the parameter. What we did here again, see, I connect the important points. Now, I did not apply the Pythagorean theory to the right triangle. I did see a right triangle there. But the problem is, how can I express, for example, this right triangle, how can I express, you know, the distance between the tangent point and the vertex? I have no idea. Okay, the only I know is the radius, right? Which is the height of the right triangle. But that's it. I cannot do anything. So this is using area. I can determine the radius of the inscribed circle. Okay. So this is a nice formula. I did not know that before I discussed this problem. I did not know this formula. Yeah, actually, honestly, we just derived it. We got this formula. Okay. And then you can repeatedly use that. It's not the same problem. You know, the problem I discussed in my lecture notes was the equilateral triangle, but I end up with the same formula. Is a isosceles triangle. Okay. All right. So today we studied the problems related to the circles, and we have one more lecture on this. Okay. And the key idea is connecting important points, and you get triangles, usually get the right triangles, and express each side in terms of the unknowns, then you apply the Pythagorean theory. Okay, except for the last one. Last one I did see a right triangle, but I couldn't apply the Pythagorean theory to the right triangle. Okay, I use the area, okay, to solve the problem.